Okay. Now that we understood the PBE methodology, let's talk about the differences that the code-based seismic design has, which we do it based on Eurocode or ASCII or ATC codes around the world, with the combination of performance-based seismic design which PBE has been implemented in it. So the code-based seismic design, the performance is implied, but there is no way to verify it. The code tells you to do this and this and this, and hopefully your structure will be safe. There is no verification, there's no assessment based on the code. And as we discussed and we look through some negative and shortcomings of the code, the codified structural systems are there is no specific behavior of your particular building. We just sum up all the types together. There's prescribed seismic demand, elastic response spectrum. There is no hazard assessment of the location that you're building your building. It is expected that the strength of your material and components to resist the prescribed applied forces. So simply the applied loads are compared to the resistance, and whether it's successful or not, then the code just ticks it without looking at how that strength is getting degraded under different earthquakes and how that load should be applied. There are some drift limits for specific forces, for example, serviceability, wind, stuff like that. And members and connections simply follow some prescriptive detailing that the code specifies. All of these come up with this problem that all of this design is elastic. We're not considering the full non-linearity of the building, and instead we used an equivalent lateral force instead of using the actual earthquake. The modal response spectrum analysis is just based on simple T1 that you get the structure, and does not implement in the behavior of the building. And then as we discussed, the nonlinearity and ductility is simply just considered using the R or the Q factor. The R is for the American types like ASCII 16, 716, and the Q is for the Eurocodes. That is the behavior factor or the discount code that we always discuss. As we discussed, the current building codes provide a design which is capable of withstanding the maximum considerable earthquake shaking and with low probability to prevent total or partial collapse. This is the whole concept that code follows. So we don't have that midpoints, and it just really goes back to how frequent the earthquake is. One of the problems that we saw was during the 2011 Christchurch earthquake, which a lot of buildings were designed based on the code and were designed to withstand the maximum considered earthquake, but they didn't perform as we expected.
New Zealand's darkest day. At least 65 people are dead, many more injured. The magnitude 6.3 quake struck in the heart of the city of Christchurch.
Pulling a body out of rubble that had fallen on a car. People with blood pouring down their faces, just walking in a daze.
No one can be alive under this. Emergency services urged people to get out of the city.
So it's just huge. It is huge.
You can just see the buildings that have lost their facade.
Australia's offer of emergency help has been taken
The danger
up.
is far
New
from
Zealand
over.
government
Here,
is to grips with the
surviving
scale
stand
of
up.
Just
destruction.
trembled again
A
and
task
then just
force
panicked
sent
everyone
to
and then they head for the outskirts of town, really, standing right in the middle of
So although the city was properly designed with the codes and followed that, but we saw a huge structural and non-structural damage. And unfortunately, even until now, the resilience of the city was so low that still the damages are there and lots of buildings have not been repaired or reconstructed. So the performance-based seismic design, on the other side, is a design approach that verifies the building seismic performance explicitly under different intensities, and based on that you can do some conclusions whether the design is sufficient for that area or not. What you are seeing is a scenario earthquake of magnitude 7.2 which is happening in California, and it clearly shows how the waves are propagating. Again, it's a probabilistic approach, and you can see the shakings. The red color definitely indicates the higher shaking. Based on this kind of modeling, you can definitely see what are the probabilities of the shakings which will be exerted to your building, and you can get always ready for that with a future plan as well, that okay, if an earthquake strikes my building, this is how it will behave, and what should I do afterward, how the repair approach should be, how much money should the stakeholders have to apply for the repair, and how much should I expect the downtime of my building. So just comparing what we just discussed based on code-based and performance-based, codified structural system only. So there is no, if you have any structure which is a little bit different, a little bit out of the specific types of the identified by the code lacks and it's not very happy with it. Prescribed seismic demand, that 475 year return period, why should we apply that? Why not 12% probability in 50 years? Why not 15% probability in 50 years? Fully elastic model, as we discussed, nonlinearity and ductility is in terms of factors, the Q factor that we apply, and very simplified analysis, equivalent static, meaning gravity analysis, and like the best case scenario is the response spectrum analysis, which the modal analysis is done, the eigen analysis is done, T1 is found, and then is applied back to that response spectrum to see what is the design response spectrum. So performance is only implemented and is not verified at all. But the performance-based seismic design, which is based on PBEE, we have a proper site-specific hazard assessment. As you saw, we can understand really what are the probabilities of different intensities in that area that we're building our building. Innovative structural systems are allowed, so systems which are not normal in the code, for example, the dampers, base isolators, or any specific type of building which is, for example, circular, which the code is not very happy with them, can be done if the performance is okay, everything is okay. We do proper nonlinear models, so ductility is not in terms of a factor, is actually inside the model, and the behavior of the components, the reinforcement, the steel, the masonry, the timber, the glass, because we have defined their nonlinear behavior and the hysteresis for their force deformation, moment rotation, stress-strain relationship, can be fully understood by the model, and we get a good output of it. And then the type that we combine this site-specific hazard and the nonlinear is the dynamic time history analysis that we do. So geometric nonlinearity and material nonlinearity, as we discussed, the hysteresis represents all of these. So at the end of the day, the performance is explicitly verified. So you get the output and you just compare it. This building under this specific earthquake will shake this much. What is the performance is clear. So the pros and cons, again, there are some advantages and there's always some disadvantage for a new method. The pros, as we continuously are saying, site-specific hazard assessment, detailed understanding of the building's performance, innovative structural systems, which can be cost-efficient lateral resistance systems like the base isolators, architectural features that prescriptive requirements do not allow. So in some cases, as we mentioned, like you want to make a spaceship but the code doesn't allow it, with a performance-based seismic design you can do that, and it's safer and more serviceable building, which definitely is better than what the code allows. But on the other side, there are some problems. One of them is it's a little bit labor intensive, so you really need to do all of those extensive analysis and you need to have the knowledge. Anyhow, I don't think you can put anyone behind Seismostruct, OpenSys and expect them to apply an earthquake and analyze the building and extract the output from it. This is what you guys are learning in this module, that okay, we will model the building from scratch, we will analyze it, we will understand how it will perform, and we will even move further. I will tell you what is the performance of your building under different intensities and conditions. Another problem of PBSD is that it needs approval. Anyhow, at the end, because you're bringing so much concepts into it, there should be some peer reviews and the approval of the building officials, while the code, because it's codified, it's just a matter of whether you follow the code or not. The peer review of this is like you have to explain exactly what you have done to not only the client but the judge as well. And it might need a little bit higher initial investment, so the cost of the engineer design compared to the cost of the construction, as well as the cost of a normal structural engineer which designs based on code, is a little bit higher. So when do we typically implement this PBSD? It's not very common yet for residential mid-rise buildings. So where we implement it is in the regions of high seismicity like Los Angeles, Tokyo, Istanbul, which have high seismicity. For high-rise buildings, if you remember, majority of those codes were actually proposed for tall buildings. Taipei 101 is one of those buildings. As you know, there is a damper on the top. This damper wasn't in a normal situation to be designed based on code. It needed a more advanced code. For example, another building is Torre Mayor, which is in Mexico City, very seismic area. So all of those had to be designed following the performance-based seismic design. Majority of critical facilities and infrastructures, you really don't want your hospitals, your fire stations, your shelters to be damaged during an earthquake. So you want to know what is their performance. Some cases which the beauty and the architectural features cannot be achieved due to the restrictions that the code implements. We will see an example. The Taipei Performing Arts Center is a good example of this. In some cases that the innovative systems and materials that are not codified, like the base isolators, there is no specific, we are coming up with some codes and stuff, but there is no specific code for just designing base isolators. And in cases that the stakeholders really are looking forward to the performance beyond the code, like they really want a stronger building. For example, nuclear reactors have to be designed very strongly, so performance-based seismic design is a good approach for them, and then you can show them what is the performance of their buildings during different intensities and different events. Let's look at some photos of the cases that we discussed. Taipei Performing Arts Center. As you can see, there is suddenly a round circle in the middle. This is not a structure that you can easily make with code, so you really need to do some nonlinear time history analysis of this. It's in Taipei as well. Very strong winds as well as earthquakes. San Francisco airport, specifically the control tower, is a very thin structure, very tall, and then suddenly a massive bit like a mass damper on the top of it. This really needed performance base. We will see at San Francisco's airport as well in a second. The nuclear reactions in Japan, majority of them are built with performance-based design. Majority of hospitals in San Francisco are built with base isolators at their bottom. So this is one of those cases. The General Hospital in San Francisco, this was built with performance-based seismic design. Just look at the San Francisco's International Airport. Is kind of a brand new airport. Very long spans. They're using a combination of trusses and columns to keep this long span. It's San Francisco, lots of earthquake, so they had to make sure that it performs very well. This is one of the steps of their design. As you can see, the model is made with SAP 2000, so nonlinearity and stuff are considered in it. They're applying real earthquakes to it, and they're measuring the deformation of the structure to see whether it's acceptable or not. The model probably is scaled up, so the deformation that you see over here is a little bit not realistic, but very simply we can see the performance of the building, and we can decide whether the number of trusses and the number of components in beams and columns are sufficient or it needs improvement. Another good example is Torre Pedregal 24. Again, it's in Mexico City as well, very seismically active. When you look at the building, you don't see anything specific in terms of resistance, while the building, as you can see, the bottom is has a very limited area. While it gets higher, the area increases. So this is not a normal building. The code really doesn't like such a irregularity in plan. And as well as if you look at the construction, you can see a massive brace, like a V brace, which is supporting the building for lateral loads. This is literally impossible without modeling as well to make sure that it's holding the building together. So proper models of the building have been built, as you can see over here. They're applying loads, and you can see like whether the brace is under extreme loading or not. And according to this, you can see like the earthquake is properly shaking the building, and according to this, they concluded that whether these braces are sufficient or the section needs to be improved or other bits should be improved. So it makes the engineer's life easier, and the stakeholders and the owners of the building can fully understand what is happening to their building under different scenarios. So in a normal situation, when you want to implement the PBSD framework, which is a expanded PBEE methodology, first of all, the designer, the owner, the building officials, they all gather and they define performance objectives. They define that under such earthquake, with this intensity or this magnitude, I want my building to be having slight damage. Under such earthquake, which has rarer occurrence, I want my building to have, let's say, extensive damage. Or at this bit, it's okay if it fails, otherwise my cost will go higher. Then according to that, you will develop a preliminary design. This preliminary design is based on Eurocode, is based on the regular codes that that country has, and it, like all the buildings follows. So after that you have designed your building, you go back to your modeling, and you model your building in different conditions. How much detailing it has, that will take different time. The more detail, the more realistic your model is, the better. And according to that, you will assess the performance capabilities. You will apply the possible earthquakes in that area, knowing the hazard of that area, have been conducting the PSHA. You will analyze your building and you'll see its performance. Now, having the performance of the building, you will just compare it. Does the design meet the objectives that you have defined initially? These objectives were defined based on different earthquake intensities, different earthquake shakings. Have they met those objectives? If not, you have to revise your design again. If yes, well done. You move on to the next step, which is peer reviewing, and the officials, the building officials should approve it. As simple as that. So the developed a the preliminary design is based on the normal codes that we have. It's nothing new. What is different is, first of all, defining some performance objective, as well as assessing the performance capabilities using nonlinear modeling and nonlinear behavior of your material as well as your geometry. So those phases can be simplified in performance objectives, site-specific seismic hazard assessment, nonlinear time history analysis, performance criteria assessment, review, and approval process. So these three is the bit which the performance that you have defined over here will be assessed. So phase 1, performance objectives. Again, you sit with your clients and you talk to them that, okay, under different design earthquakes that I have, very frequent earthquakes, kind of occasional, rare earthquakes, very rare earthquakes, what do you want your building to perform? Do you want it to be fully operational, functional, life safety, near collapse? For example, we have a rare earthquake, extreme earthquake, 970 years return period, very big one. You want your nuclear facility to be here. You want your nuclear facility to be fully operational. But do you want your hospital to be here as well? Probably yes. Or you might want to have a residential building. Do you still want a fully operational residential building under a very rare situation? That can be achieved, but then the cost of that design will be very high. So that's where the stakeholders' opinion matters as well, because they are the client, they are going to pay for the project, and they have to decide whether economically it is okay for them or not. Imagine you have a new building. Some of these performances, the design performance levels, are not acceptable. For a frequent earthquake, your building should always be fully operational. You cannot have a frequent earthquake and you have a life safety damage. That is not a good design. That is not acceptable. For let's say a rare earthquake, we always want our building, our new residential building to be life safety. Somewhere here. So depending on the how the building is it standard occupancy building like residential, commercial, or is it a critical facility like a hospital or shelter, or if it's a life-threatening facility like a nuclear reactor, depending on that, you have to define what is the performance you want under different earthquakes. Now that you have defined your performance, you go to the initials. You look at the site-specific seismic hazard assessment, whether it's available or not. If it's not, you have to do a PSHA, you'll do a probabilistic seismic hazard assessment of the location, and according to that, you will get some conditional mean spectrum or uniform hazard spectrum out of the PSHA. In the next session, we will discuss about this and how you can develop a uniform hazard spectrum from the PSHA that you have instead of the code response spectrum which the Eurocode or ASCII or ATC suggests. So it's very specific to your location. And I'm sure you all remember the steps that you were doing for PSHA. You were going from the site to the recurrence relationship, to the attenuation relationship, and at the end to the hazard curve. From the hazard curve, you can get a uniform hazard spectrum or conditional mean spectrum in some conditions. Now, having some earthquakes which match to that response spectrum, you apply it to your building. Now, your building can be modeled in 3D, in 2D, with as much as details as possible. And Under the nonlinear time history analysis, you get some outputs: deformation, which is mainly for the performance of the structure; acceleration, which is mainly for non-structural components. Now, this model can be a black box. What happens in it and how detailed you have, it really depends on how much you want to spend time on it. The more time you spend, the more time the analysis takes, the more details it will have, and your results will be more realistic. We will discuss the components of this analysis in more details, but for now, remember that the analysis types that we can follow is the normal nonlinear time history analysis that we apply an earthquake to it, the cloud analysis that we apply a lot of random earthquakes, incremental dynamic analysis, and multi-stripe analysis, which we scale some earthquakes, some limited number of earthquakes, but with different intensities. And depending on how detailed your model is and how much nonlinearity is considered in all of the elements, you can have very realistic performance of your building or very limited performance of your building. These really depends on how capable your software is and how much experimental results have been implemented in it to act as realistic as possible. You have designed your building, you extract the results, you understand how the structure is performing. This is where the fragility and the vulnerability comes in, and this is where you will peer review your performance. If it was approved, perfect. If not, you have to revise it. So can the performance objectives that you have defined in the initial stage been achieved? Yes or no? Now, if you remember, in one of the cases it was saying that considering the resilience of the structure and following the PBEE methodology, the price of the structure can go up 10% something. Here is a good comparison between a normal structure designed based on code and a structure designed by performance-based seismic design. So the concept design, both of them are the same price, so it's nothing added to the performance-based because the same engineer will design it. The schematic design can have a little bit added, the design development definitely a little bit added because of the analysis involved in it. The construction documentation as well will be added as well. Anyhow, it's a heavier work and it's a little bit harder. So all of these normal prices for a structure, this much will be added to it. Remember, this is just the design phase. The construction is separate price. So at the end, about 18% to let's say 15% will be added to the initial price. That if you wanted to design your building based on code, you have to pay 15% more to shift it to a more rigorous and better performance based on the PBEE design. To just end this lecture, let's look at a sample project which PBSD has been implemented in it. This is Torre Reforma in Mexico City. This is that building. The building beside it is Torre Mayor, which Torre Reforma is a newer building, let's say. It was completed in 2016. It's about 250 meters high, 57 floors. And it is in Mexico City, so extremely earthquake prone. If we look at the building, first of all, you can see to make just stuff extremely sophisticated. There is an opening over there. You can see the braces. One side is fully facade, so seems like everything is like a balcony. You see there is the core of the building, and all of the floors, like a balcony, like a cantilever, are connected to the core. So it was a very sophisticated design, and it wasn't something to simply be designed based on codes. Different usage, you can see offices, there's a fitness center, there's some plaza and some parkings in it. So as you saw, there is a main core which all of the floors are connected. These floors are supported with trusses at the bottom as well. So very sophisticated design, and different components coming together. So really the only solution is to do proper 3D analysis of the structure to make sure that everything is going as expected. So let's look at some renderings. The different components of the structure have been modeled separately, and these take a lot of time and a lot of investment, but this is the only solution to make sure that such structure withstands any type of earthquake which is possible in that location. Over here I'm just showing two types of earthquake which have been applied to the structure. As you can see, one of them is for service level, one of them is maximum considered earthquake, the maximum possible earthquake that the structure should withstand. And accordingly, different analysis has been done, story drifts, roof drifts, all of these have been considered, and results like this comes up, which hopefully most of them are in blue. Usually blue is good, red is bad. So in this case, they're just comparing the performance of different components of the building to what limits that ASCII has. ASCII, the American Society of Civil Engineers, the code that they were following, they're just comparing it. And as you can see, it is fully operational. Some bits and pieces have reached to immediate occupancy, but it has, with all costs, have avoided very high collapse prevention or complete collapse, which is good, and the structure has been approved. So with all of that, I'll leave you with some good sentences from the architects of the PBEE framework, Professor Alan Cornell and Helmut Krawinkler, which we saw just one of the nonlinear models that he proposed. And next sessions we will discuss about him more. He was a professor of Stanford University as well. And what they're saying is that the final challenge is not in predicting performance or in estimating losses, but in contributing effectively to the reduction of losses and improvement of safety. It is easy to get obsessed with numbers and analytical procedures, but neither is useful unless it contributes to this final challenge. So all of those fancy models, the thousands that you do, all of those detailed models that we built, 3D, 2D, whatever, none of these matters as long as they are toward reduction of losses and improvement of safety. So with all of those, I'll end this very long lecture on performance-based earthquake engineering and performance-based seismic design. In the coming sessions, we will go into detail for every single component of this PBE methodology, and we'll get into details of how every single one of these steps are applied in a real-time situation and real cases. So thank you very much. Hope you learned something new, and we'll see you later.